Good. So last time we started off on chapter 4, and we began our discussion of aromatic compounds. And as I think you'll recall, my main goal that class day was just to get us out of that class understanding benzene is not an alkene, even though you can draw it with what certainly looks to be double bonds. Those are not ordinary double bonds, but because the double bonds are delocalized, this is why you can also draw it with a circle, which is meant to remind us that, you know, those 6 pi electrons are delocalized. It falls short because you can't tell just by looking at the circle that there's 6 electrons involved. Here you can easily see 2, 4, 6 in the 3 pi bonds there. But what this is very good at reminding us of is that benzene is not an alkene. And as to which you personally use, I don't really care. I think they will tend to use this type of thing in OWL. And as I said, on my printed material, you'll see in my exams and in my class notes that I will tend to draw it like this, because ChemDraw, as well as the sketcher on OWL, I don't think make it real easy to use the circle. That we have a good question of here. This says circle will always be 6 electrons. Well, that's just it. For benzene it is. But if we changed it to a ring of a different size, you see maybe not. That's the problem. So the circle will always be 6 electrons. I would say yes for benzene. But if you see other circles, I don't know if we'll ever run into them, but that might not be 6 electrons. That's the weakness of the circle. But I think the good overcomes the bad. I tend to draw it like that, but if you would rather draw benzene using this or the other Kekule structure, go right ahead. They're both perfectly acceptable. The circle will be at least 6. No, if the ring is smaller than a 6-membered ring, then it's going to be fewer than 6 electrons. I don't know that we're going to really run into those all that much anyways, but certainly for benzene, the circle means 6 electrons. I think that's at least fair enough to say. Good, so we figured out the structure of benzene. We learned that it's a resonance stabilized species. Oh, and by the way, before I forget, everyone, please register your attendance. I'm not going to do polling today. I had some questions prepared, but I honestly think they'd be better on Friday after we've seen some of this material. Good. Yeah, but do register your attendance. It'll be a free 10 out of 10 for attendance once I get in there and fix the Reef gradebook, which, as I've said, stinks. So I'll download those scores and make sure everyone gets the credit they should. Okay, so where was I? So we figured out the structure of benzene, that it's a resonance stabilized species, and that's why benzene is not an alkene. And I sort of want to save the reactions themselves mainly for next time. I just kind of want to take it slow, especially since we've just had an exam. And if I read it right, it sure looks like we have through Friday to finish chapter 4. Yes, we do. I don't need to start chapter 5 until Monday. So I'm going to take advantage of that. Yeah, not an alkene. If we got that out of the first lecture, we're doing well. That was my main point. So benzene is not an alkene, and as we're going to start to touch on today, that means it's not going to act like an alkene. In chapter 3, we said CPDs, compounds, shorthand for compounds. I also sometimes do, I do CPD for compound. I also like to do RXN for reaction. So they're just common abbreviations. Good, so we covered how alkenes behave in chapter 3. There we learned that alkenes undergo addition reactions when you treat them with a variety of electrophiles, as we call them, Lewis acids, basically. Lewis acids and electrophiles are the same thing. There you go. 2 words meaning exactly the same thing. So organic chemists just love that for some reason. And what we'll find, though, is that benzene does not undergo addition reactions with electrophiles. It will react with them, although interestingly, you've got to kick them quite a bit harder than you've got to kick alkenes. Why? Because they're a good deal less reactive, because it's so stable, being a resonance stabilized species. But if you kick them hard enough, you can get benzene and other aromatic compounds to react with Lewis acids with electrophiles. But now we're going to find they don't undergo addition reactions. They undergo substitution reactions. And we'll have more to say about that later, but I think we've already defined substitution or displacement reactions. Likely you talked about types of reactions in Gen Chem. And there's really like maybe 4 overall types of reactions, not including the redox distinction, you know. And some reactions are redox and some are not, right? It's perfectly possible for a reaction to be neither oxidation nor reduction. That's pretty common as well. But apart from that distinction, what are your 4 types of reactions? Like substitution, elimination, addition, and addition and elimination are opposites, and then rearrangement. That's just basically something turning into an isomer of itself. And I think all the reactions are going to fall into those 4 categories, and we'll go over all of them as we get to them. But we've already talked a good deal about substitution and addition reactions. And then if you understand what an addition reaction is sort of like A plus B yields AB, and you know, 2 or more things come together to give you one big one. Well, elimination is just the opposite. They're reactions of the type AB goes to A plus B. Something splits up into 2 or more parts. So those 2 are opposites of each other. Meanwhile, substitution involves something hopping off of one molecule and onto another. So one type looks sort of, in a general sense, looks kind of like AB plus Y goes to A plus BY. The B jumps over. Those are more usually inorganic. But there's another type that can be either inorganic or organic. It's kind of like AX plus BY goes to AY plus BX. The 2 things switch. And that's very common. You saw scads of reactions like that in Gen Chem. All of your precipitation reactions are double displacements, are substitution reactions of that type. Sodium iodide plus lead-2 nitrate yields sodium nitrate aqueous plus lead-2 iodide precipitate. Those are, it's like the metals switched places. So, and we're going to learn that benzene and related compounds undergo reactions that actually are kind of like that. There's going to be 2 pieces that switch places. One of the pieces, I'm sort of getting ahead of myself here, we'll mostly cover this on Friday. One of the pieces is going to be one of the hydrogens on the benzene ring. And that's going to switch places with something on the other molecule, on the Lewis acid, on the so-called electrophile. But very different reactivity. That's the main upshot of what we talked about on Friday. Since benzene is not an alkene, we must not be surprised when it behaves completely differently from alkenes. And so, we're gonna touch on that today, I think. But before we go into that a little further, I'd kind of like to take care of nomenclature of aromatic compounds. First of all, I think you'll find there's a table on page 118. I'm 95% sure it's 118. Just let me check my notes and make sure I'm not lying to you. Yep, page 118. There's a table there of various mono-substituted benzenes, meaning that we start with benzene, we take away an H and replace it with something else. And it's about 9 compounds, and you know me, I'm not normally a fan of memorizing stuff, but those compounds are so common, and derivatives of them show up so often in all kinds of consumer and industrial products, and in biological molecules, that I really do think it's worth your while to know them. So things like methylbenzene, we normally call toluene. Benzene with a carboxylic acid functional group, we call benzoic acid, right? Benzene with an OH group, we call that phenol, P-H-E-N-O-L. Or with an aldehyde group, I think I've talked about that compound, benzaldehyde. So these are just such common compounds that just show up everywhere. I really think it would, in this case, be worth your while to memorize those names and put them together with their structures. That will also help us to name other benzene derivatives. One thing, though, before we even get that far, we need to recognize that there's this possibility for constitutional isomers here. Because as soon as you put 2 groups on benzene, whatever those 2 groups are, whether they're the same or different, I think you'll agree there's 3 ways to do it. The 2 groups can be right next to each other. They can be in kind of a 1-2-3, 1-3 relationship to each other. Or they can be directly across the ring. That'd be a 1-4 relationship. 1, 2, 3, 4. So all three of those are possible. So that means we need to be prepared for that when naming. And you can call these 1, 2, 1, 3, and 1, 4 disubstitutions respectively. That's not wrong. But these also have other names that you're also going to need to know. The 1, 2 disubstitution pattern is also called ortho substitution. O-R-T-H-O. And sometimes they even just put O for ortho. They'll abbreviate that further. 1, 3 disubstitution is also called meta disubstitution, M-E-T-A, as in that's so meta, or M for short. And then 1, 4 disubstitution can also be called paradisubstitution. And now that I think about it, I don't really know where those are coming from, or P for short. They look kind of like Greek to me. I expect they came from the Greek, but why those words, I couldn't tell you. I don't know any Greek. But these are other ways of naming them. And we'll, if not always, we'll at least usually find that that either one of these can be used to come up with a correct name, that both are equally acceptable. So for instance, we'll start with an easy one. Let's take our benzene and put 2 chlorines on it next to each other. Well, you could call that either 1, 2 dichlorobenzene, in other words, coming up with a name like that, you don't really need to know anything else other than what you learned from naming alkanes. That name's pretty straightforward, I think. Or you could also call it orthodichlorobenzene or O-dichlorobenzene. These names are equally correct. Neither one is any better than the other. And you will not be able to convince me otherwise. I think those 2 names are equally correct. Perfectly acceptable, both of them. We'll do other examples, but does that make sense so far? Any questions so far? Well, let's take a look. Let's do this one. And I might have to erase a little bit in order to make some room. Let's just for fun put an aldehyde functional group over here. And by the way, just in case, I think I've already mentioned how carboxylic acid functional groups can be abbreviated CO2H or COOH. This molecule, without adding anything else to it, you can also abbreviate the aldehyde group as CHO. I just want you guys to know that just in case you run across it. But CHO is a common abbreviation for an aldehyde functional group. The reason we write CHO instead of COH is, well, then OH makes it look like it's an alcohol. So I don't care if you use these abbreviations. That's all of these abbreviations that I tell you about, it's optional. You can use them or not as you please. All I ask is that when you see them, you understand them and you know what they mean. So I thought I'd tell you that just in case you run into that abbreviation. But we're not going to have just plain benzaldehyde. We're going to put one of those over there, otherwise known as an isopropyl group. So you could call this, this would be named as a benzaldehyde, since the way you know that is before we put the isopropyl on, that molecule is a name by itself, benzaldehyde. It's one of those 8 or 9 or 10 compounds that are on page 118. And so if you see one of those groups, typically that's going to take precedence. So we will name it as a benzaldehyde, and we'll point out, although I could have drawn it a little better, we'll point out that the isopropyl group is in a 1-3 relationship to the aldehyde group, with the carbon bearing the aldehyde group being automatically considered carbon 1. So you could go either way with this. You could call this 3-isopropyl benzaldehyde, And again, you don't repeat the 1 because it's assumed, it's understood that the carbon bearing the aldehyde group is carbon 1. Sorry, Chad, I'm going to have to move you over. So that's one thing. Or you can use this meta thing. You could call it meta or M isopropyl benzaldehyde. Either way is perfectly fine. I see no difference between those names. They're both perfectly acceptable. And here the M is expressing that the isopropyl group is in a 1,3 relationship with the aldehyde group. There you go. So that's just a couple of examples, and I have a few more. I even have a tri-substituted case. But I really don't care which of those naming conventions you use, ortho, meta, para, or just numbers. And I don't know about always, but I do believe you'll find in the vast majority of cases, you can use either and come up with a perfectly good name. Good. Any questions on either of those two names? Was it necessary to put the 1 on the dichlorobenzene? Well, yes, because if you just, you can't, if you didn't, you'd have to say something like 2-chlorobenzene, and that sounds a little weird. Aldehyde is higher precedence for numbering. Yes, because benzaldehyde is a compound that has its own name already. So that's why I think it's worth knowing those 9 names or so that are on page 118. And those will show you the ones where you have to do this. Those will show you the ones that have a group that takes precedence. And even there's still sometimes multiple possibilities for how to name something. But I do think it's better to use those, I can maybe almost remember them. I know there's going to be toluene, I know there's going to be benzaldehyde, I know benzoic acid. I think they tell you how isopropyl benzene is called cumene. Come on, Jack. Phenol, did we say phenol? What else? I don't really know if they'd want to count bromobenzene or chlorobenzene or nitrobenzene. Those are pretty obvious. I just don't have that whole table memorized. I'm just trying to think of some others. They may get into the xylenes, the dimethylbenzenes, but all those names are so common that I really do think they're worth your learning. Whoops. Good, so let me clear a bit of space. Can we call it benzaldehyde no matter what carbon has CHO group attached? It does, if there's only, in other words, if there's only the aldehyde group, then yes, it doesn't matter because all the positions are the same. And the way you know that is if I put it down here. That's a good point. I don't want you all memorizing that the group goes at the top right. I can put it down here, and that's still benzaldehyde. The way you know that is you can just turn the molecule and you'll get this. So the one-word answer to your question is yes, you call it benzaldehyde if it's just a monosubstituted benzene with an aldehyde functional group. And it doesn't matter where you put it, it's the same thing. Does that make sense? Can everyone see that it doesn't matter where you put it, it's all the same thing? Because you just turn it and you'll get the same thing. Make sense? Any other questions about that? This might take a bit of time, but luckily time I've got. I'll leave that page 118 over there. All right, I have a few more examples that I think will get us through the worst bits. Did you say OM and P are constitutional isomers? Yes, and the way you know that is because it's a different connectivity. right? In order to be stereoisomers, it is the same connectivity. All the types of bonds are the same in both molecules. And that's not the case when the two groups are on different carbons. They're connected up differently. So that's how you know they're constitutional isomers. They fall into that definition. Let's see. Oh, I want to do one that's harder than that. I was going to give you Paradiethylbenzene. That's too easy. You guys can draw that one on your own. Let's do that. So, and again, could you be perverse and name that as a substituted ethylbenzene, p-hydroxyethylbenzene? I guess that name's not terrible, but I would hope that that the OH would take priority. That's another one that's on the table in page 118, phenol. So I really do believe that's best named as a phenol. And you see we've got an ethyl in the para position or 4 position, and you can use either. You can call that either 4-ethyl phenol, and again, you don't need to say one phenol because it's understood that carbon 1 is going to be the one that has the OH group. The name phenol takes care of that for us. Then you can sure call that 4-ethyl phenol, or if you'd rather call it para or p-ethyl phenol, fine. I think both those names are equally correct. And I really have no preference for your preference in that matter. You can use whichever you like. But as to 4-hydroxyethylbenzene, I mean, it's not raw, it's not terrible, but I think this name is a little bit better. People would know what you mean, but they'd be like, what a strange thing to call it. It's not a -1,000 type error. It might be a -1 type error. I think these names are better. Yes, having an OH group attached to the benzene makes it phenol, period. Not phenol group, but phenol is the name of that compound. Oh, and a word on phenol, we'll probably talk a little bit more about it later when we cover alcohols. One of the things we'll learn about phenol is, yes, it's an alcohol, but it's special. It's quite different from aliphatic alcohols like ethanol or isopropanol. It's a good deal more acidic for one, and we'll get to that later. But phenol has been used for a century plus in consumer products. It was used to make what I believe, double check me on this, but I think it was the first commercially used plastic, Bakelite. You got to go back to like 1920. Yeah, phenol is incorrect. It's phenol. It's F-I-N-N, oh, I just made this up. O-L-E, F-I-N-N-O-L-E, phenol. That's how we pronounce it. But yeah, it's normally not pronounced phenol. Good. Where was I? Oh, right, Bakelite. So you'd have to look that one up, but it was the early part of the 20th century that Bakelite first came out. Phenol has also been used as an antiseptic in hospitals. I don't think they use it so much for that anymore, but it was used that way at one point. And even today, if you go to the drugstore or the supermarket, you can get that sort of original Listerine stuff with that sort of brownish, has that medicine-y taste. I think it's dreadful stuff. I remember my dad used that. He swore by it. I thought it was just awful, but you can still get it to this day. And the reason for that medicine taste is because of the phenol. It doesn't have a lot in it. I mean, phenol is a little bit toxic, yes. So I wouldn't go drinking a bottle of Listerine, not that I'm too worried about any of you wanting to do that. But at those concentrations, a few percent, it's not going to harm you. And it is an antiseptic, so it makes sense to do that. Good, so there's that one. What if you've got a tri-substituted example? Or, wait a minute, this one's actually tetra-substituted. Woohoo, aren't you excited? No, Jack, just you. Let's put a methyl there. Put fluorines here. And maybe, oh, just for fun, let's put a propyl group over there. Not isopropyl, but regular propyl. So which of these groups is going to take precedence? I kind of think the methyl will, because methylbenzene, no one calls it methylbenzene, everyone calls it toluene. So if we call that carbon 1, the one that has the methyl group attached, looks to me like 2, 3, 4, 5, 6 is the most logical way to number that. And I think you'll get the same answer if you number it in the other direction. So I think we'll want to say that the propyl group rather is on carbon 4, and we've got 2 fluorines or fluoro on carbons 1 and 6. F comes before P, so I think we would want to call this guy 2,6-difluoro. What, 4-propyl toluene. I think that's the best name. There may be other ways to name it, but I think that's the most straightforward and clearest name. Can we number other ways? Well, you'll get the same thing. Then this will be 2, 3, 4, 5, 6. You'll get the same answer. So if you didn't get the same answer, then you use the same rules as we learned when naming alkanes, which is you pick whichever name is the smaller sum when you add up all the numbers. But in this particular case, it doesn't matter which way you go. You'll get the same thing. So the one-word answer to your question is yes, you can do that. You'll get the same thing. Good, so I think that's the best name. At least in my opinion, I think that's the best name. So that's how you handle polysubstituted benzenes. Now, you can't do anything with orthopara meta because there's more than 2 groups. So orthopara and meta only work if there's exactly 2 groups attached, like this. Then you can use those. If you have any more than 2 groups, then we need to toluene. Yeah, sorry about that. Whoa. Toluene, there we go. So, forgot what I was going to, yeah, orthometa and para only work if there's exactly 2 groups on the benzene. Any more than 2 and you have to use numbers. But I think you can see, learning how to name alkanes, most of that stuff transports over here just fine. And you use the same rules, even to name these things. Where did you get the toluene? Because it's methylbenzene. There's a methyl group up here. See this stick coming out over here? That's a carbon over there. So you need to know that methylbenzene is toluene. That's on page 118. That's going to be one of the ones that I suggest you guys memorize. And I don't love students memorizing things, believe me, but I think it's worth it in this case because those compounds are so common. They show up everywhere, and derivatives of them also. So, good. What looks like a 1? I can rewrite some things if it's not clear. Is that better? Is everyone okay in the name now? Anything I should rewrite? The top carbon, the carbon that the methyl's attached to is carbon 1, and here's the methyl group. If you wanted to draw it in, which you could, you do it like that. So the carbon is attached to carbon 1 of the aromatic ring. The reason it's carbon 1 is because we're naming it as a substituted toluene. And the way you know to do that is because toluene is one of these compounds in the table in page 118. Oh, I see. Well, we can fix that. It's never too late. There we go. More better. So, any other questions on that name then? Do I have another one for you? Oh, not exactly, but I do want to deal with this. It looks perfect, I'll tell you. Oh, no. There is one other thing. Your book doesn't quite emphasize this as much as I would like it to, because this is something troublesome. And it's one of these things that we're stuck with. And I've put this in your class notes. And it is the use of this word benzyl. It's a darn shame, but a benzyl group is benzene ring or phenyl group CH2. And then that can be attached to whatever. That is called a benzyl group. And it's a darn shame. That's why I, wait, Benzyl. It's confusing, and it's very unfortunate, because when you use the word benzyl, it makes it sound like like something is coming right off the benzene ring, but it doesn't work like that. So for example, and just to emphasize, it doesn't have to go on the top right carbon. If you had this compound, CH2Br, that compound would be called benzyl bromide. There, did it again with forgetting my Z. Benzyl bromide, and it's a shame. I'm only making such a big deal out of it because it is so confusing. And I mean, this was decided early in the 20th century. None of us was around, not even me, to protest it. So unfortunately, we're stuck with it. So just remember when you see that word benzyl, it's referring to benzene plus one more carbon. And you can call carbons of this type benzylic, that would be fine. You can say the hydrogens on that carbon are benzylic hydrogens. I don't know that we'll ever need to do that, but those are examples of where you'd see that word. Or to give you another example of a benzylic type compound, CH2OH. That compound is known as benzyl alcohol. And benzyl alcohol is a very different critter from phenol. Benzyl alcohol is much more similar to methanol, ethanol, isopropanol, all those guys, than phenol is. But I mean, you see why this is confusing. Benzyl bromide sounds like it should be this. At least if you're not careful, it sort of sounds like it should be this. But that is not benzyl bromide, that is bromobenzene. So it's a darn shame, but we're stuck with it. And I just wanted to kind of get a warning out there to you guys that this is out there and it's potentially confusing. So I just wanted to help you to avoid problems with that. So I don't know how much we're going to use the word benzyl, but it will pop up here and there from time to time. And I just want you guys to be aware, that red flag should go off. Careful, it's not coming directly off the aromatic ring. It's coming off a carbon attached to the aromatic ring. And there are scads of compounds of these type also. So that's just an unfortunate historical feature of nomenclature of aromatic compounds. So like I said, my main goal here is just to warn you guys this is out there so that you don't get confused by it. Good, and I think that's all I'd really like to say about nomenclature. While we're pausing, everyone please do register your attendance. Any other nomenclature questions? I mean, as usual, I think it's best that you practice. That's how you'll really learn it, but I'm happy to answer questions. You mean I did it again? I'm such a good teacher. And that, oh, you had one about the first set of drawings. Well, we can go back to it if you, I think I have in my notes what I drew back there. Let me just make some room. Well, I mean, we have time. We have 10 minutes left. I would like to take 5 to 7 minutes just to sort of, trying to figure out the propyl group. Oh, okay. What did I draw there? What did I have that had a propyl group? I think that was the one with all the fluorines and everything else, right? Yeah, I think we had. Oh, 3-isopropyl benzaldehyde. That was this guy. So basically what you need to know is this shape, this piece over here is an isopropyl group. The reason it's called an isopropyl group is because there's 3 carbons in it. And what makes it isopropyl is it's attached to the middle carbon. It's attached to carbon 2. So that's what makes it an isopropyl group. Oh, they can be. Absolutely they can be, but then it's not an isopropyl group. Then it's a propyl group. And that's a thing. You can certainly draw that compound. 1, 2, 3. So this is 3-isopropyl or M-isopropyl benzaldehyde. This would just be 3-propyl or M-propyl benzaldehyde. And they are different compounds. So there's 2 different types of propyl groups. Just like there's 4 different types of butyl groups, but really there's 2 of them are much more common than the other 2, the N-butyl and tert-butyl groups, which we introduced in the alkanes chapter. Good. So let's see. So like I said, in my remaining 9 minutes, all I would really like to do is just get us set up to talk about the electrophilic aromatic substitutions. And I think the best way to do that, if you can stand a little bit of history, and trust me, I think history is my weakest subject, to my shame. I am not proud of that. But sometimes a teeny bit of it is in order. And this gets back to what we were saying about benzene not being an alkene. And all I mean when I bring up history is the sorts of things they found out at first about benzene. We already know, for instance, that alkenes will react with HCl, HBr, HI, quite readily, in fact. And we talked about how you can know what the structure of the product is, how you take the double bond and turn it into a single bond, and then one of those former alkene carbons gets the H, the other gets the halogen, ClBr iodine. And the way you know which gets it is by Markovnikov's rule, if appropriate. And alkenes are very, very reactive to HCl, HBr, and HI. That goes like a shot. Benzene, no reaction. NR for no reaction. We said that alkenes can react with elemental halogens. Chlorine and bromine, anyway. And the way you get the structure of the product is you turn the double bond into a single bond, and you add chlorines to both of those formerly alkene carbons. Benzene, once again, if you add chlorine to benzene, they just look at each other, no reaction. So clearly something unusual is going on here. Next time we will find that, in fact, you can get benzene to react with chlorine or bromine, but you have to add a catalyst. It has to be either aluminum chloride or iron 3 chloride. And even then you don't get an addition reaction, you get a substitution reaction in which we replace one of the benzene hydrogens with a chlorine. And the same thing would work if it were Br2, you'd replace it with a bromine. And of course the other product is HCl. So you see, it's just like I said, this is not an addition reaction, this is a substitution reaction. One of the H's on benzene and one of your halogen atoms of Cl2 or Br2 switch places. It's not addition, it's substitution. So we'll get into that next time, but these are the sorts of reactions we're going to see. I might have a little more to say about that in a moment, but I really just want to put a cherry on the top of this, so to speak. You might have heard about the permanganate ion, MnO4- in Gen Chem. It's a beautiful purple color. It is also one of the strongest oxidizing agents known to man. It'll chew up anything. If you added KMNO4 to either an alkane or an alkene, it'd just chew it all up. And you'd have nothing left but CO2 and water. The carbons would all go to CO2 and all the hydrogens would go to water. But you can, and it's usually sold, by the way, as the potassium salt, so potassium permanganate. KMNO4 will oxidize anything except benzene. No reaction. Chemists were astonished when they found this stuff at first. And this just backs up what we said before, that benzene is not an alkene. Alkenes would for sure react with potassium permanganate. And only if you were very careful would you be able to get just one clean product. Most likely it'd just chew it all up. It's a stupidly strong oxidizing agent, but not towards benzene. Benzene is too stable even to react with potassium permanganate. So again, the idea that I'm trying to get across here is clearly benzene is special, and again, clearly benzene is not an alkene. There's something else going on. Benzene will react with some of these things, and we'll learn some of those. We'll learn those reagents the next time. We'll learn about the so-called electrophilic aromatic substitution reactions, but they require much harsher conditions. They often require catalysts, and even when they do react, you don't get an addition reaction. You get a substitution reaction. So benzene's a completely different animal from alkenes. Let me just see if I had more to say about that. Yeah, I guess there's a little bit more I can say. I want to compare alkenes undergoing additions to aromatics undergoing substitutions. Any questions so far? That will then be my last point, and if we get out a minute or two early, it's not the end of the world. Yes? What does aromatic, what, sorry? Well, for us, it's going to include, what does aromatic include? It's going to include benzene and derivatives of benzene. So benzene and benzene with other groups on the ring. As I might have mentioned, are there other compounds besides that that are aromatic? Yes. I don't know that we're going to run into them too much. Let's see. Anyone else then? Any other questions? Oh, and there you go again. Aromatics are also called arenes. There you go. We're never happy unless there's at least two words for the same thing. I really don't know why that is, but it does seem to be in general true. Okay, so what we learned in chapter 3 was essentially that alkenes in general, and I'm just doing a generalized alkene over here, I'm not even being specific about what's attached to the two carbons. We learned that these readily would undergo addition reactions to give addition products looking something like this. And these types of molecules typically were electrophiles or Lewis acids. Lewis acids and electrophiles are the same thing. There's these two sets of words, Lewis acid, Lewis base, that one we know already. And there's also electrophile, nucleophile, which we'll cover more in detail, I think, in chapter 6. But just to let you know, those words are out there, and I can come up with no important distinction between an electrophile and a Lewis acid, or between a nucleophile and a Lewis base. I couldn't tell you what the difference is. I think they mean the same thing. Why two sets of words? I don't know. Yet another one of this class is full of things that we're just, this particular class today, I mean, is full of things that we're stuck with, and that's another. But when you treat alkenes with electrophiles, we learned they tend to undergo addition reactions, and you get products of this type. But that's not so for aromatic compounds. Aromatic compounds, undergo substitution reactions when you treat them with electrophiles of this type. And again, this will usually require a catalyst, which just shows you how unreactive benzene and benzene derivatives are. And even then, you don't get an addition reaction, you get a substitution reaction. So you'll replace one of those 6 hydrogens with this electrophilic group. Doesn't matter which of the 6, they're all the same. And you will, in general, also get some kind of byproduct, often a hydrogen halide. So that might be HCl or HBr very typically. Maybe not always, but typically something like that. Normally, we don't really care about the inorganic byproduct also. We're focused on the organic product. So these are the types of reactions we're going to learn next time. And we're, just so you know, we're only going to overgo the reactions of unsubstituted benzene. We're not going to cover directing effects. I've left some questions of that type in OWL just so you get exposure to it, but I don't really care if you guys learn all those ins and outs. I don't mind you being familiar with the idea, but like I said, I'm not going to make you come up with your own directing effect answers on your own. But I think we'll make that clear the next time. I'll try my best to make it clear what I will expect of you. And there's areas that touch on directing effects that I think you can get the answer even without knowing about them. So that's what we'll cover next time. Other than that, I'm out of time. So have a good day. We'll see you all Friday.